sklearn, random projection, Johnson-Lindenstrauss MINDM. Description: this function calculates the minimum number of dimensions required to embed a dataset into a lower dimensional space while preserving pairwise distances within a given error bound. Using the Johnson-Lindenstrauss lemma. Inputs: n samples the number of data points in the original dataset. This is an integer representing the number of rows in the dataset. Apes the desired error bound. A number between 0 and 1, representing the maximum acceptable distortion of pairwise distances in the embedding. Smaller values of apes result in more accurate embeddings but require a higher dimensionality. Outputs: MINDM, the minimum number of dimensions required for the embedding, calculated based on the inputs n samples and apes. This integer value represents the number of columns in the embedded dataset. Steps: the function utilizes the Johnson-Lindenstrauss lemma, which guarantees the existence of a dimensionality reduction technique that preserves pairwise distances within a given error bound. It calculates the minimum number of dimensions based on the desired error bound apes and number of samples n samples. Metrics: pairwise distance preservation. The primary metric is the preservation of pairwise distances between data points after dimensionality reduction. The error-bound apes defines the maximum allowed distortion. Dimensionality reduction factor: the ratio between the original dimensionality and the reduced dimensionality, indicating the extent of compression achieved. Visualization plots: scatter plots visualizing the original data points and their corresponding points in the embedded space can demonstrate the preservation of pairwise distances and the distribution of points. Heat maps comparing pairwise distance matrices in the original and embedded spaces can visually assess the similarity between the two representations. Fine-tune parameters: apes adjusting the error-bound apes influences the trade-off between accuracy lower apes and dimensionality reduction higher apes. Uncertainty methods: Monte Carlo simulations running multiple embeddings with different random projections can assess the variability of the dimensionality reduction process and provide confidence intervals for pairwise distance preservation. Challenges and fixes. Challenge 1: choosing inappropriate error-bound apes is crucial, as a too small value may lead to a large number of dimensions while a too large value may result in significant distortion. Sample use case that resulted in challenge 1: trying to reduce the dimensionality of a dataset with a high number of samples while aiming for a very small error-bound apes might lead to a prohibitively large minimum dimensionality. Fixes to challenge 1: experiment with different apes values to find a suitable trade-off between accuracy and dimensionality reduction. Consider applying domain knowledge to guide the selection of apes. Challenge 2: handling datasets with high intrinsic dimensionality, where the data points are inherently complex and require a large number of dimensions to represent, can be challenging for dimensionality reduction techniques. Sample use case that resulted in challenge 2: applying the Johnson-Lindenstrauss lemma to a dataset with a high number of features and complex relationships between data points may result in a substantial loss of information due to the dimensionality reduction. Fixes to challenge 2: consider pre-processing techniques such as feature selection or dimensionality reduction using other methods, e.g., PCA, before applying the Johnson-Lindenstrauss lemma.